Let me show you one example. For example, we can consider U subset of the vector space V, which is the polynomials in X, and let U to be the subspace of polynomials such that the degree of polynomials is less than 4, and also the polynomial satisfies that P of 0 equals to P prime at 0 equals to 0. And find a polynomial P in U such that the integral from 0 to 1, 2 plus 3x plus minus px square dx is as small as possible. So that means is minimal. So what we have here is inner product. PQ inner product is just the integral from 0 to 1, P of x times Q of x dx. And then we have this V vector, which is actually the function of x, which is 2 plus 3x. So this is an element of the V space, which is the polynomial space. And then the inner product that we want to minimize with this notation is actually the norm square of the difference between V and U vectors. For function spaces, let's not write out the vector notation. Let me just write V minus U norm square. And we want to minimize this. So minimize for U from the subspace U. We need some kind of form for this U subspace. It has a degree less than 4 polynomials. So in U, the description of U is P of x should be, let's say, A0 plus A1x plus A2x squared plus A3x cubed. So the degree is less than 4. That means maximum is 3, the degree. But then we also need that P of 0 is 0. P of 0 is A0 if you substitute x equals to 0. Then we have that the requirement for the subspace U is that P prime at 0 is 0. So P prime x is A1 plus 2 A2x plus 3 A3x squared. And then from here we have that P prime at 0 is A1, and that's supposed to be 0. So with this we get a better description of U. U is just polynomials P of x such that P of x equals A0 and A1 are 0, so we're left with A2x squared plus A3x cubed. And we know that there is a basis in U. We have done this before. For polynomials, the basis, we can just choose the monomials with the degrees x cubed, x squared, and x cubed. The only thing is that this is not orthonormal, but otherwise this is the same problem that the theorem is about, that we have a V space, which is all the polynomials. We have a U subspace, which is some special polynomials. We have a V vector, which is 2 plus 3x, and we want to minimize the distance between the V vector and the P polynomials that are from this subspace U. So for that, the process says that this minimal will be the orthonormal projection. So the solution is supposed to be P of x, which is the orthogonal projection onto U of the V vector. And for that, for the orthonormal projection, we need the orthonormal basis. And this is the Gram-Schmidt process to normalize, orthonormalize this. E1 is just x squared divided by the norm of x squared. The norm of x squared, so this is coming from the inner product, which was defined as 0, 1, x squared times x squared dx. That's x to the 4, and the integral is x to the 5 over 5, evaluated at 0 and 1. So this is 1 over 5. That's 1 over square root of 5. So that means that E1 is x squared divided by 1 over square root of 5, which is square root of 5x squared. And then the second one, E2, first we calculate the unnormalized version, which is the next vector x cube, x basis element, x cube minus x cube inner product with e1 times e1. So we have to calculate the x cube inner product e1, which is the integral from 0 to 1, x cubed times square root of 5x squared dx. That's square root of 5x to the 5, so this will be x to the 6 over 6 from 0 to 1, and that's square root of 5 over 6. With this, e2 star is x cubed minus square root of 5 over 6. e1, that was another square root of 5 times x squared. So this is x cubed minus 5 over 6 x squared. Then we have to normalize it. For this we need to calculate its length, which is again the inner product by itself, and that's the integral from 0 to 1. We also have to take the square root of the inner product for the norm. So this is the square root of the integral from 0 to 1, x cubed minus 5 over 6 x squared dx. A little integration practice. Note that the only way to integrate this is if we expand the square. So we get x to the 6 minus 5 over 3 x to the 5 and plus 25 over 36 x to the 4. This is just squaring out, expanding the square. And then we integrate. We get x to the 7 over 7 minus 5x to the 6 over 6, so that's 18, plus we get x to the 5 over 5, so that simplifies the 25 over 36. And from 0 to 1, at 0 everything cancels out. At 1 we get 1 over 7 minus 5 over 18 plus 5 over 36. The common denominator is 7 times 36, and this is then 36 minus 10 is 16, 36 minus, so this 14 times 5, this is 70, and this is 35. So altogether this is 1 over 7 times 36, the length. And then with this, E2 is E2 star divided by the norm of E2 star, which is x cubed minus 5 over 6 x squared divided by 1 over 7 times 36. Yeah, and I forgot to take the square root. So this is actually square root of 7, and the 36 has square root 6 times x cubed minus 5 over 6 x squared. So once we have the orthonormal basis, E1, E2, orthonormal basis, then we get that the solution is the projection of U, or a projection of V onto the U subspace, which means it's V inner product with E1 times E1 plus V inner product with E2, E2. So we have to calculate these inner products. V inner product E1 is the integral from 0 to 1. 2 plus 3x is the v vector, and the e1 vector, the basis vector, is square root of 5x squared dx. And we have to calculate this again by multiplying it out first. So this is the integral from 0 to 1, 2 square root of 5x squared plus 3 square root of 5 x cubed dx. Then integrating we get 2 square root of 5 x cubed over 3 plus 3 square root of 5 x4 over 4, evaluated at 0 and 1. Only the 1, the upper limit, stays, the other one cancels out, and we get 2 square root of 5 over 3 plus 3 square root of 5 over 4. And perhaps we could take the common denominator, which is 3 times 4, 12, and we get then 8 plus 9 is 17 square root of 5. So this is the coefficient of the first E1 basis vector, and then V inner product E2 is the inner product 2 plus 3x with the E2 vector, which is 6 square root of 7 x cubed minus 5 over 6 x squared dx. And again, we would have to multiply this out to get some coefficients. So this is supposed to be a number, but this is now becoming more and more tedious. Using the FOIL multiplication, you're supposed to multiply it out and then integrate. Yeah, so at some point there is no problem to do it with a computer, for example with Mathematica. Otherwise, it's a routine but long calculation. So the final answer supposed to be, you can double check that, it's 24 x squared minus 203 over 10 x cubed. So the interesting thing is that if you plot these two vectors, the 2 plus 3x vector, the original one, and then this p vector, the picture is something like this. So this was the v vector, the original vector that we wanted to approximate. So you might say that, well, this is nothing close to it, but note the serious constraint was that in the U subspace, we had that p of 0 is 0, and the derivative of p at 0 should be also 0, which is nothing like what the original function was. So this orthogonal projection is doing the best it can. Another example I want to show is the least square solution to linear systems. So what we have is that AX equals B linear system sometimes has no solution. Actually, many times it doesn't have solution. So then what we might be happy to find the X vector such that AX minus B norm, or norm square, which is the same, just squaring it, doesn't change the minimum property, so it's minimal. So if this is in Rn, then the norm is calculated with the 2 norm. So this is the 2 norm, and the 2 norm, the Euclidean norm, is calculated using the sum of the squares. That's where the name least squares is coming from, that this norm is actually the square norm, 2 norm. This AX minus B is usually denoted by R, that stands for the remainder. And in fact, A doesn't have to be even square. So if A is m by n, then X vector is from Rn, and then the result B will be in Rm. And what we have is that AX is an element in the image space of the A matrix, or we can also say that this is the column space of A. This is a subspace of Rm, showing a similar picture as before. We have the Rm space, we have the B vector, and then a subspace of this is the column space or the image of A. And again, what we want to do is we want to minimize the distance between this B vector and the A vector. And this will be if we use here the projection of B onto the image. Let's denote it with U, following the previous notation. So by the way, we also have this residual, so the other name for remainder is that residual vector. So we also have that in the best case, when we have the projection, then this residual vector is actually this vector. So the distance between the vectors pointing from B to the subspace. That means that the residual vector is orthogonal to the image of A, or we can say that the residual is in the image of A perp. Let me emphasize that this is the column space of A. So this really means that R is perpendicular to the columns of A. This is a vector in Rm, and the columns of A are also vectors in Rm, because A is a m by n vector. So that means that the way we can write out the inner product is two m vectors, that will be the dot product. So A has columns. Then one way to write down the dot product with the columns of A is to write actually A transpose times the residual vector, because then we get an n by n matrix multiplying a n by 1 vector. So we have the columns multiplying the r vector, and we just collect these together. So this is supposed to be the 0 vector, because when we transpose A, we get the columns as rows. So these are the columns of A as a row vector. And all these columns supposed to be perpendicular to R, so when we multiply the residual, we get the 0. If you write this out, that you multiply with the A transpose AX minus B, and that's supposed to be the 0 vector, we can rearrange it and we get that A transpose AX equals to A transpose B. So these are called the normal equations, and you see that that comes from the fact that we have orthonormal vectors. The residual is orthonormal. And then it turns out that this we can solve, and that will be the optimum, the minimizing x. A transpose A is, so originally we had n by m, and A is m by n, so this is a n by n matrix. This is now square matrix, and actually it's also invertible. So this was derived basically using the idea of this minimization technique, but actually you don't really see the projection explicitly. It ends up to be just solving a linear system. So an example for this: 2 minus 2 minus 2, 2, 5, 3, 3 by 2 matrix times x equals 16 minus 4 minus 7. So you can see that this is not solvable if you start solving it. There is no solution. Yeah, you get only 2 pivot entries, and the third row you're not going to have a 0 row, because no 2 rows are linear combinations if you take the augmented matrix. So instead of solving it, we solve for the least square solution that gives the least error. So here A is the 2 minus 2 minus 2, 2, 5, 3 vector. B, or matrix, B is the 16 minus 4 minus 7 vector, right hand side vector. Then we need A transpose A, 8 plus 25, 33, 7, 7, and 17. We also need A transpose B, which is, this is 32 plus 8 minus 35, and minus 32 minus 8 minus 21, which is 5 and minus 61. So then the normal equations: 33, 7, 7, 17, and it's augmented by the right hand side 5 and minus 61. And then if you solve this, it turns out that the solution to this is x1, x2 equals to 1 minus 4, the least square solution. So the residual can be small or large depending on how far this B vector is from this subspace, the column space of A. Let's not calculate the residual. Even if it's large, that doesn't mean that we did a bad job. It just means that our constraint was so severe. So the idea is that this subspace U actually serve as some kind of constraint that prohibits us to completely reach B. We must stay in the U subspace, and then we have to do the best we can to approach B, or to approximate B. So this is the end of this section about orthogonal projections and minimization, and the last section will be 8.4, linear functionals and adjoints.